The Bernoulli equation for an incompressible steady fluid flow. In 1738, Daniel Bernoulli formulated the famous equation for fluid flow that bears his name. The Bernoulli equation is a statement derived from conservation of energy and work energy ideas that come from Newton's law of motion. An important and highly useful special case is where friction is ignored and the fluid is incompressible. So please remember the condition, which is the friction is ignored. So friction is ignored means the nature of the fluid is ideal fluid. So means there is no resistance due to the viscosity effect, and the fluid is incompressible. So means the density is not changed. This is not as unduly restrictive as it might first seem. The absence of friction means that the fluid flow is steady, that is, the fluid does not stick to the pipe side and has no turbulence. Most common liquids such as water are nearly incompressible, which meets the second condition. Consider the case of water flowing through a smooth pipe. Such a situation is depicted in the figure below. We will use this as our working model and obtain Bernoulli equation employing the work energy theorem and energy conservation. So the model is like this one. So for example, we have a pipe from the bottom here flow to the upper level like this one, and then the diameter of inlet is bigger and the diameter of outlet is a little bit smaller. So and then we could create, or we could draw a free body diagram like this one. Okay, so for example, to push, when we imagine that how fluid moving inside a pipe. So for sure you need some kind of force to push the liquid from point 1 here, then it will flow to point number 2 here. So when you push it, okay, so we will have a pressure. So means that to have a force, so we assume that there is a pressure at point number 1, and we have a cross-sectional area of A1 here. And then at the same time, so another pressure could occur on the surface, as we learned previously. So it is the pressure should act on this surface. So we create that because the fluid is moving. So there is another pressure at the outlet here to resist the flow. So we draw P2, push the area here from right to the left, and then the cross-sectional area here is A2 because the cross-sectional area is not the same. So and then because the cross-sectional area here is bigger, so means that the distance of the displacement from the original surface to the new surface after certain force being pushed on this surface can be assumed as x1. So and then because it is incompressible, so means that the fluid here is not compressed itself, so means that the same amount, the same volume would be transferred here, would be moved at the outlet. So because the cross-sectional area here is smaller, so we assume that the displacement distance here, the displacement is larger compared to the displacement at the inlet here. So we draw a little bit longer arrow, the longer area at the outlet here. So your free body diagram can be written like this one. So we have a pressure 2 pushing the surface from right to the left, and pressure 1 here pushing the surface from left to the right. We examine a fluid section of mass M traveling to the right as shown in the schematic above. the total work W done in moving the fluid is this one. So W total mean work total. Work done in this situation is work 1 plus work 2. So work 1 here mean work at exit, work at inlet plus work that occur at outlet. So work can be described as force times x, force times displacement. So we could write as F1 x1 minus F2 x2. So why we have a minus F2 here? Because it acts on the opposite direction. So in this equation, equation number 1, where F denotes a force and x a displacement, the second term pick up its negative sign because the force and displacement are in opposite direction. Pressure in the force exerted over the cross-sectional area, or P equal F over A, rewriting as this, F is equal to PA, and substituting into equation 1, we could find it will become like this one. So as stated here, if we replace the force here with equation with pressure, so we could write as equation number 2 here. The displaced fluid volume V is the cross-sectional area A times the thickness x. This volume remains constant for an incompressible fluid, so we could write as this one, which is V, the volume, is equal to A1x1 equal A2x2. So and then we could replace into this equation. So we could find that equation 3, based on equation 3 and equation 2, we could have delta W, means the work done in the system, it is equal to P1 minus P2 times the volume. So we denote this one as equation 4. So and then, since work has been done, there has been a change in the mechanical energy of the fluid segment. This energy change is found with the help of the next diagram. So this diagram will explain about the idea of energy change. Okay, we know the energy change between the initial and final position is given by this equation. So we could see that the total energy, or means the energy difference, is about the potential energy and also the kinetic energy at the outlet minus with the potential energy and kinetic energy at the inlet. So according to this diagram, you could know that in normal condition, water cannot go to a higher level because the energy is not enough. So means that if water could flow to the higher level like this one, so means that it will create, or it will have higher potential energy because the distance here is different. So and then the kinetic energy means the energy that comes from the velocity of fluid itself. So and then we could write this term into this one. We know that the potential energy is mgh and the kinetic energy is 1 over 2 mv square. So we substitute the subscript of 1 and 2 to acknowledge the outlet and inlet here. Here, the kinetic energy K, which is 1 over 2 mv square, where m is the fluid mass and v is the speed of the fluid. The potential energy U is mgh, where m is the mass, g is the gravity, and h is the average fluid height. Normally, when we analyze flow in pipe, we will take the center point of a pipe as our h here. The work energy theorem says that the net work done is equal to the change in the system energy. This can be written as delta E is equal to delta W. So the idea of this one is the work can be done because there is energy changes from one point to another point. So from our diagram, we could say that the work can be done because potential and kinetic energy change itself. So it's something like this. I think you already know. At inlet here, maybe the kinetic energy is higher but less potential energy. And then when it travel to the higher level like here, so the kinetic energy will reduce, but the potential energy will increase. So mean the changes of energy could create work. So and then we substitute the equation of delta E and delta W here, work and energy, into equation 6. So we could write like this one. And then we dividing equation 7 by the fluid volume and replace m over volume with rho. It will give us this equation, equation number 8. So we rearrange the equation number 8. We just put all the inlet value, means equation with subscript 1 and at the left, and equation with subscript 2 at the right. So we could rewrite the equation 8 here into equation number 9. Okay, in some textbooks, you will find that people will write this equation like this one. So instead of pressure plus 1 over 2 rho v square plus rho gh, people will write like this one. So it will become P over rho g plus v square over 2g and plus h1. So 1 here means inlet and 2 here means outlet. So in some textbook, they will replace the alphabet H here, the denote H here, with Z. That's why in certain textbook, you will see the Bernoulli equation become like this one. Finally, note that equation 9 is true for two positions. So please be careful about this condition of Bernoulli equation. Therefore, equation 10 is commonly referred to as Bernoulli equation. Keep in mind that this expression was restricted to incompressible fluid and smooth fluid flow. So means that it is only can be used for incompressible fluid. Normally for water, oil, we use a Bernoulli equation, and for smooth fluid flow means we assume that there are no resistance, no high resistance occur on the flow. So if in certain textbook, they will also write like this one, P over rho g plus v square over 2g plus z equal constant. So what it is mean by constant here? So it is means that the total energy is same. Total energy is constant. So this equation is called a Bernoulli equation. So I hope you could remember this Bernoulli equation because it is not given in the test or final exam. So normally people will remember this equation. To use it correctly, we must constantly remember the basic assumption used in its derivation. So assumption number 1 is viscous effects are assumed negligible. So means there are no slip condition and so on and so forth. So mean there is no resistance. And number 2, the flow is assumed to be steady. So mean there are no changes of velocity in terms of time. Number 3 is the flow is assumed to be incompressible. So means that the density is not changes. Then the equation is applicable along a streamline. So means that the idea of this one, number 4 here, is closely related to idea of this constant. So I will explain about this in example later on. Because it is you need to check the streamline first before you could apply or before you could derive your Bernoulli equation. So if Bernoulli equation is integrated along the streamline between any 2 points, indicates by suffixes 1 and 2. So you could write like this one.